Okay, let's dive right into this explainer on gas tungsten arc welding. This is a precision process that fundamentally transforms how we build and shape our modern world. If you've ever marveled at those incredibly clean, seamless joints on a high-performance bicycle frame, or maybe on some aerospace components, well, you are likely looking at the magic of this exact technique. So today, we're going to break down exactly how the whole shebang works.
Here is our roadmap for today. We're going to cover 1. Introducing GTAW. 2. The invisible protective blanket. 3. Anatomy of a TIG setup. 4. The GTAW advantage. And finally, 5. Applications and unexpected hazards.
Section 1. Introducing GTAO.
So the absolutely crucial point here is that GTAW, which you've probably heard commonly referred to as TIG welding, uses a non-consumable tungsten electrode to generate its intense electrical arc. Now, unlike other welding methods where the electrode itself literally melts away to become the filler metal, the tungsten here stays completely intact. It acts strictly as the torch that delivers the heat. It's an electrical arc maintained perfectly between the tip of that tungsten and the metal part you're trying to join.
But, heat alone just isn't enough. When metals melt, they actually become highly vulnerable to contamination from the air around us. So imagine a perfectly invisible blanket being fed right through the welding torch, continuously protecting the entire operation. This inert gas completely shields the heat-affected zone, the actively molten metal, and that tungsten electrode itself from the surrounding atmosphere. It really is an elegant solution to a pretty chaotic physical process.
Section 2. The invisible protective blanket.
We hear the term inert gas tossed around a lot in manufacturing and chemistry. But what exactly makes a gas the perfect, invisible bodyguard for molten metal? Why do we pump this specific gas over the weld?
Well, the answer lies in its complete chemical apathy. An inert gas is totally inactive. It's deficient in active chemical properties. It simply does not burn. The defining feature is that it adds absolutely nothing to and takes absolutely nothing from the metal it's protecting. Gases like argon and helium are perfect for this just because they completely refuse to chemically react with other elements. Plus, they're totally transparent and odorless. This is absolutely vital because it gives the welder maximum visual clarity to see the precise arc they're manipulating. Though, as a fascinating little caveat, sometimes a tiny bit of a reactive gas, like hydrogen, is strategically added just to boost the travel speed of the weld.
Section 3. Anatomy of a TIG setup.
Let's anchor all these abstract concepts to the actual physical machinery you'd see out in the real world. Take a moment to trace the lines here. You can clearly see the central power source, the coolant system block over on the right, and that crucial tall shielding gas cylinder on the left. All of these distinct systems converge seamlessly right down into the torch held by the operator.
Following the physical path, we can see exactly how the circuit is completed. First up, the power flows from the terminal through cable 1 to a water-cooled copper contact tube, which holds our non-consumable tungsten electrode. And yes, it literally requires that water cooling because the heat generated is just that intense. Second, the circuit is completed because the workpiece itself is grounded to the other terminal via cable 2. Finally, step 3 shows our invisible gas blanket traveling directly through the torch body, expertly directed by a nozzle straight down over that blindingly bright weld pool.
Section 4. The GTAW advantage. Now, when you compare this directly to older or different methods like shielded metal arc welding, the GTAW process is vastly superior when it comes to air protection. But here is the real game changer. Because GTAW relies entirely on that invisible gas blanket, it doesn't require any flux. And with no flux, there is absolutely zero slag left behind. Slag is that crusty byproduct that usually forms over a weld. By eliminating it, we completely remove anything that could obscure the welder's vision of the molten pool. The result? Unparalleled precision.
This process is also incredibly versatile. Thanks to that focused arc and easy current control, we can do things that are usually notoriously difficult in metallurgy, like joining completely dissimilar metals. I mean, imagine smoothly welding copper directly to brass, or stainless steel directly to mild steel. Plus, the precision creates a very narrow heat-affected zone, which translates to significantly less structural distortion. It's an absolute must-have for very thin metals. Ultimately, it yields vastly improved metallurgical properties, leaving you with joints that are stronger, more ductile, and highly resistant to corrosion.
Section 5. Applications and unexpected hazards. Depending on the specific metal they're targeting, welders kind of have to act a bit like chemists, carefully selecting their gas mixtures.
If you're welding aluminum alloys, a straight mix of argon and helium is the standard go-to. But when dealing with stainless steel or nickel alloys, welders will actually inject a 5% mix of hydrogen into the argon. We touched on this earlier. Adding that tiny reactive element physically increases the arc's heating efficiency, allowing the welder to move faster and lay down a much cleaner bead on those tough materials.
But here's the catch. Staring into what is essentially a miniature sun, mere inches from your hands, has a pretty wild, unseen consequence. That electric arc is so incredibly intense that it emits powerful ultraviolet radiation. This UV light is literally so strong that it actually physically breaks the chemical bonds of the normal oxygen molecules in the surrounding air. When those oxygen atoms recombine, they form hazardous ozone gas right there in the immediate vicinity of the arc. It's a stark reminder of the extreme physical forces at play here.
Which leaves us with a really fascinating final thought to ponder. When we deliberately harness such extreme sun-like power for industrial creation, achieving miraculous feats like fusing dissimilar metals and building our aerospace infrastructure, what other hidden, invisible footprints are we leaving behind in the very air around us? It's a brilliant intersection of human engineering and raw atmospheric chemistry. Thanks for joining us to explore the hidden mechanics behind the world we've built.